Good morning. My name is Omar, and today I will be presenting our experiment on the acceleration of a cart on an inclined plane. The experiment is based on Galileo's discovery that objects' acceleration down an incline due to gravity, and that this acceleration depends on the angle of the incline, not the mass of the object. The main objective of this experiment was to measure the experimental acceleration of a cart moving along an inclined air track and compare it to the theoretical acceleration. We also investigated how changing the mass of the cart and changing the incline angle affected the acceleration and percent error. So a little bit of the background and theory. When an object is placed on an inclined plane, gravity acts downward towards the Earth. However, only a component of gravity acts parallel to the incline and causes the object to accelerate along the track. This component of acceleration is given by the equation A equals g, which is gravity, by the sine of theta. When g is gravitational acceleration, which is approximately 9.8 meters per second squared. The sine of the angle was calculated using triangle geometry. Sine theta equals opposite divided by hypotenuse. The opposite side represents the height of the incline, and the hypotenuse represents the length of the track. The length of the track that we use will always be equal to 1 meter. This equation predicts that the acceleration depends only on gravity and the incline angle, not the mass of the object. Experiment and setup. The experiment included an air track, a cart, also called a glide, a metal slab to adjust the angle, a motion sensor, and the capstone software to collect and analyze the data. The air track was tilted by placing the slabs under one end, which created the incline. The height of the slab was measured to determine the opposite side of the angle, and the length of the track was measured to determine the hypotenuse. As mentioned before, the hypotenuse is always constant, keeping at 1 meter. When using these measurements, we calculate the sine of the incline angle and then calculate the theoretical acceleration using the formula A equals g sine of theta. The motion sensor was calibrated so it can detect the cart moving along the track. Capstone was set up to record position versus time and velocity versus time graphs. Now let's take a look at the experiment firsthand. So for today's lab number 5, we're going to be utilizing the exact same materials, except we're going to be changing the angle of the track. So the way we changed the angle of the track was by adding these two weights, which is increasing this height compared to this side. When we increase the height, we have angle theta right here, and we need to find the sine of angle theta to calculate the theoretical acceleration.
So in today's experiment, for the materials used, we used a track, an air blower, a motion sensor, a cart, weights for the cart, a computer with capstone program, and an object to increase the track's height to create the slope.
Before conducting the experiment, the research team made several predictions. Let's go live to our physics analysis to walk us through those expectations.
Hi, I'm Alejandra. I'm on the field here with the expert Tesla, and I'm going to interview her about the experiment. So, are you expecting a different acceleration when mass change?
We did not expect a significant change in acceleration when mass increased. Um, the mass cancels not out during the deviation. The mass acceleration on the incline plane depends only on gravity and the angle of the incline, not the object of the mass.
If yes, how will it change?
So, in the ideal frictionless system, acceleration should stay the same, and any small difference will likely be caused by experimental uncertainty, friction, or measurement variation, not by the added mass itself.
Are you expecting a different percent error?
We expected a percent error might change slightly. Adding mass can sometimes reduce the impact of the friction or of the sensor, but the difference should not be dramatic if we did it well.
Now the experiment is complete. Let's analyze the results. Thank you, Tesla, and I pass the mic to Omar.
For Table 1, we calculated the theoretical acceleration for the first tilt. using an opposite height of 0.030 meters and a hypotenuse of 1 meter. We found that sine theta equals 0.030. Multiplying this by gravitational acceleration, 9.8 meters per second squared, gave us a theoretical acceleration of 0.294 meters per second squared. This value represents the acceleration predicted purely by physics, assuming no friction and ideal conditions. In Table 2, we calculated the experimental acceleration for the cart using the 0.030 meter tilt with the original mass. The cart started from rest and reached 1.0 meters per second in 3.8 seconds. Using the change in velocity over time, we calculated an acceleration of 0.282 meters per second squared. When compared to the theoretical value of 0.294 meters per second squared, the percent error was 4.1%. This small percent error indicates strong agreement between experimental and theoretical values. For Table 3, we repeated the experiment using the same tilt but added 10 grams to the cart. The cart accelerated from rest to 0.66 meters per second in 2 seconds, resulting in an acceleration of 0.330 meters per second squared. Comparing this to the theoretical value of 0.294 meters per second squared gave a percent error of 12.2%. While this error is larger than in the first run, the acceleration remained close to the theoretical prediction, supporting the idea that acceleration on an incline is independent of mass. In Table 4, we increased the tilt of the track by raising the opposite side to 0.045 meters. This increased sine theta to 0.045. Using the equation of equals g sine theta, we calculated a new theoretical acceleration of 0.441 meters per second squared, compared to the original theoretical acceleration of 0.294 meters per second squared. This represents a 50% increase. This confirms that acceleration increases proportionally with the angle of the incline. In Table 5, we measured the experimental acceleration for the higher tilt. The cart went from rest to 0.96 meters per second in 2.05 seconds, giving an acceleration of 0.468 meters per second squared. Comparing this to the new theoretical value of 0.441 meters per second squared resulted in a percent error of 6.1%. This close agreement further supports the relationship between incline angle and acceleration.
Imagine a skateboarder at the top of a large ramp at a skate park. At first, the skateboarder is standing still at the top of the ramp. The ramp is tilted downward, creating an inclined plane. As the skateboarder begins to roll down the ramp, gravity pulls them downward along the slope. At first, the skateboarder moves slowly, but as they continue going down the ramp, their speed increases more and more. This happens because the skateboarder is accelerating due to gravity. The steeper the ramp is, the faster the skateboarder will accelerate. If two skateboarders of different masses start from the same point on the ramp, they will accelerate down the ramp at almost the same rate, even if one skateboarder is heavier than the other. The acceleration caused by gravity on the incline will be nearly the same for both. This example demonstrates Galileo's idea that acceleration on an inclined plane depends mainly on the angle of the slope, not the mass of the object. Just like the cart in the experiment, the skateboarder speeds up as they move down the ramp, showing how gravity causes acceleration on a tilted surface.
Overall, our data supports Galileo's conclusion that acceleration on an inclined plane depends on the angle of the incline and not on the mass of the object. Increasing the tilt increased acceleration as predicted by the equation as equals g sine theta. A equals g sine theta, while changing the mass produced only small variations due to the experimental uncertainty.
And that's it for lab number 5, guys. Thank you to our scientist, Galileo, for having us look at gravity. Have a great weekend.
I would like to thank Omar for being the creator of the graphs, the host/news reporter, and for the introduction for the video. Tesla for being our physics scientist who answered the questions. Mark for being the data analyzer who went into detail about what our data actually meant. And Alejandra for being our on-scene reporter. And of course, I was the video filmer and editor for this project.